begin our program with an introduction from Carnegie President Eric Eisen.
Thank you, and I'm very pleased that all of you can join us today as we have this conversation with Carnegie staff scientist, Dr. Sally Tracy, when we're going to hear more about how she's using cutting-edge experimental techniques to learn more about the origin and evolution of the Earth and the planets in our solar system and beyond. You know, it's been less than 30 years since scientists here at Carnegie and around the world have first found evidence that for exoplanets, planets that are around nearby stars. NASA now has an archive that lists over 4,700 confirmed exoplanets and about 3,500 exoplanetary systems. Here at Carnegie, our exceptional telescopes in Chile make it possible for our astronomers to glean information directly from some of these planets. But Dr. Tracy and her colleagues use laboratory experiments to understand the planets, the chemistries in planets, the conditions at their centers, at their cores, and on their surfaces, both deep inside and the surfaces. She also uses some of the nation's largest major facilities, like the Advanced Photon Source, Synchrotron Source at Argonne National Lab, and the Free Electron Laser Source at the Stanford's National Accelerator Lab. In some of her most recent work, Dr. Tracy has been studying the physics and chemistry of meteorite impacts here on Earth. Here she's investigating the ways in which these powerful impacts alter the minerals at the landing site when they hit the planet's surface. But to mimic these events, she takes tiny mineral samples and she uses intense shock waves, what's sometimes called dynamic compression, to put them under very high pressures. These are the pressures that will mimic the core of the Earth. She then uses lasers and X-rays, like at the facilities I mentioned, to look inside these minerals at the ways in which this high pressure shock can affect the sample's properties, its crystal structure, its phase stability, elasticity, and deformation behavior. Now, some of these changes that occur, they occur very short time, just billionths of a second, that's a nanosecond. So Dr. Tracy has developed ultra-fast experimental techniques to make sure that she can probe in these very extreme conditions, the very fast changes that are occurring. Dr. Tracy joined Carnegie staff as a staff scientist in 2019, and she came to us at Carnegie from Princeton University, where she was a postdoc. She earned her bachelor's degree in physics at Occidental College, and then spent a year working at Los Alamos National Lab in New Mexico, before going on to Caltech, where she earned a master's and a Ph.D. in material science. So like all of you, I'm looking forward to hearing Dr. Tracy talk about the ways Carnegie scientists are learning more about the forces that shape planets and their interiors, and how that information may inform our understanding of how planets form and evolve, and possibly even support life. So please join me in welcoming Sally Tracy. Sally?
Okay. Here we go. So you see my slides?
Yes, Sally, we can see them.
Okay, great. Perfect. Okay, well, thank you, Eric, so much for the introduction. I'm really excited for the opportunity to share some of my research in this sort of more discussion-based forum. And so my plan this afternoon was to tell you a little bit about how we use these so-called dynamic compression methods to explore material properties at ultra-high pressure temperature conditions in the laboratory, and hopefully give you a flavor for the type of scientific questions that we can address using these techniques. So as Eric mentioned, my interests really lie in studying materials in extreme environments, and in particular, understanding the structure and properties of materials at high pressure. So for me, high pressure physics is a super exciting field because it really allows us to fundamentally alter the character of a material in the laboratory. And this is due in part to the fact that pressure or compression really presents a really wide range of experimental tunability. So generally, when I'm talking about pressures, I'm interested in something on the order of tens of gigapascals or GPa, up to thousands of GPa. So to give you a sense of scale, one GPa is 4 orders of magnitude greater than the atmospheric pressure we experience on the surface of the Earth. Whereas the center of the Earth is believed to be at around 360 GPa, and Jupiter's center is believed to be around 4,000 to 5,000 GPa. So pressures within this range are really particularly interesting in that the energy changes associated with this degree of compression can really be on the order of chemical bonding energies. And so in this way, using pressure, we can really alter the structure and bonding of materials, which really opens the door, for example, for the discovery of novel materials, as well as the discovery, for example, of new physics. And so my recent work has primarily focused on characterizing what is sort of the atomic level structure of materials in extreme environments, in particular, looking at their crystal structures. So actually, most solids can be described as crystals, and this simply means that the atoms that make up their structure are arranged in a repeating 3-dimensional pattern, where the atoms are held together by what can be thought of as sort of a scaffolding of electronic bonds between those component atoms. But what happens when we change the pressure or the temperature of the system is there's a tendency then for a material in certain cases to undergo what is called a phase change, in which this sort of electronic scaffolding wants to lower its energy by reconfiguring, in which case the atoms are forced into new arrangements, forming what are oftentimes new and distinct structures. So of course, one familiar example of this is carbon, where on the surface of the Earth, we know that carbon favors a graphite-like structure, which is composed of sheets of carbon atoms. And these sheets sort of cleave off in planes readily from one another, making graphite a soft and flaky material. However, when we subject graphite to the intense pressure temperature conditions found deep in the Earth, these sheets of carbon will tend to reorganize themselves into what we know as the diamond structure, which is actually a tightly bonded 3-dimensional network that has very, very different physical properties than graphite being the hardest known material. So this pressure that's required to transform graphite to diamond is on the order of 20,000 atmospheres, where an atmosphere is equivalent to 14.7 pounds per square inch. Where, as the unit would imply, pressure is simply the effect of exerting a force over a given area. So if we're talking about trying to generate high pressures in the laboratory, typically what we can do is we can either increase the force that we apply, or alternatively, we can decrease the area over which that force is exerted. So the typical method then of generating high pressures in the lab is to take a small sample and squeeze it in a press-like device. And so the current state of the art for this type of measurement uses a device known as a diamond anvil cell, which is actually a technique that was pioneered here at Carnegie in the last 50 years or so. And with this instrument, what we do is we squeeze a sample between the tips of 2 gem quality diamonds, where the small area and the high strength of diamond then allow us to generate very high pressures on the order of pressures that we'd expect to see in the center of the Earth. However, as it turns out, this type of so-called static compression isn't the only way to generate high pressures in the laboratory. And much of my recent research has actually instead focused on a different technique known as dynamic compression, which is really exactly what it sounds like. And in these experiments, what we do is we generate a transient high pressure state in a material, which we achieve by sending a shock wave or a rapid compression wave through our sample, either by using an impact launcher device or alternatively with high intensity pulsed lasers. So before I jump into the technical aspects of these experiments, for those of you who may be unfamiliar with the idea of a shock wave is really just a traveling mechanical disturbance that gives rise to a step-like increase in pressure, density, and material velocity as it moves through a material. So effectively what's happening is that the material is moving at a speed that's so fast that the adjacent material in front cannot really get out of the way fast enough. And so what you see is a pileup of material in front of the source. So that's our high density, high pressure state. And so in order to sort of demonstrate this general idea, this cartoon depicts some sort of train accident that can be thought of as analogous to a shock wave traveling through a material, where here, after the impact or the train crash, the shock front travels through a material at a speed which is faster than any of the given train cars that are piling up behind it in this high pressure state. And then finally, of course, at later times, we know that this high pressure state is only transient, and we always get a release or a rarefication wave catching up with the shock front, which is shown here as the caboose expanding out backwards in yellow. So what can we learn from these types of laboratory shockwave experiments, and why do we do them? As it turns out, shock experiments have wide application in Earth and planetary science, in part being a useful tool to investigate things like natural impacts. And of course, this includes things like studying impact craters and meteorites, as well as, for example, understanding the large-scale giant impacts that likely played a role in the early stages of planetary formation and evolution. But in addition to this, because with these methods, we can generate what are really extreme pressure temperature conditions, we can actually achieve significantly higher pressures than what's possible with those static compression experiments I discussed using diamond anvil cells. And so as a result, these experiments using dynamic compression actually provide what's the sole means of experimentally accessing the interior conditions of planets that are larger than Earth, making them a really important experimental tool. In addition, though, to these applications to Earth and planetary science, these also have important engineering applications as well. For example, the development of materials for things like armor or impact coating, for example, coatings on spacecrafts, as well as things like the development of materials for high power optical applications. So how do we go about generating shock waves in the lab? One means of doing this is using an instrument known as a two-stage light gas gun, which is shown schematically here. And with this sort of cannon-like device, we can accelerate projectiles to very high velocities, up to around 7 kilometers per second or so. And so that's around 20 times faster than a typical rifle would fire a bullet, so very fast. And so this, how this works is that we have a charge detonation, and that drives our piston into a gas-filled pump tube, which is filled with a light gas, either helium or hydrogen. And that gas is then compressed to some threshold pressure, at which point you have a rupture disk that bursts, and that rupture just separates the gas-filled pump tube from an evacuated launch tube. And when that gas then expands into the launch tube, it launches an impactor, which is accelerated down the barrel to high velocities and then strikes our sample in the target chamber. And so for obvious reasons in these experiments, we have a habit of calling our samples targets and each of our experiments a shot. So it turns out that these types of gas gun experiments are not the only way to generate high pressures. And actually using high-powered pulse lasers is another technique which is really valuable as well. So when we use this method, what we do is we use these high-powered lasers to generate an ablation-driven compression wave in our sample. And so here we use a pulse laser, which we focus on the rear of our sample. And typically what we do is we affix what we call an ablation layer to the back side of our sample, which is oftentimes just plastic. And when we focus the laser onto that ablation layer, that forms a plasma, and that plasma expands backwards. And when that happens, that sends a shock wave forwards into our sample through a sort of rocket-like effect. And as it turns out, this type of laser drive compression has really started to drive the ultra high pressure frontier since it came onto the scene 15 to 20 years ago. And this figure here illustrates the peak pressures that were achieved using various experimental methods over the last 100 years or so. So from this, we can see that static compression methods, including the diamond anvil cell, have steadily increased in pressure over the last 100 years. And now it's fairly routine to achieve pressures of around 300 GPa, which is close to what we'd expect at the center of our own Earth. However, in around the 1960s, these gas gun methods came onto the scene, which are shown as these purple triangles here, which represented a big jump in the possible pressures that we could achieve experimentally. And I'll note that this y-axis is a log scale, so this is a significant jump. And this was then followed by the development of other dynamic methods, including nuclear impulse power techniques. But it's really within the last 15 years or so that we've seen the advent of these laser-driven compression methods, which are these blue triangles, which have really pushed the high-pressure science field to previously uncharted territory. And of course, this highest pressure point at the top here is from the biggest laser in the world, which is the National Ignition Facility, which is a high-powered laser facility at Lawrence Livermore National Lab, which can generate just amazing pressures up to tens of thousands of GPa. The caveat, however, with this type of dynamic compression or shock loading experiment is that, as I mentioned, the high pressure state is really transient. And so we're starting to look at what are incredibly short loading durations. So for a typical gun-based experiment, they typically last on the order of a microsecond or a millionth of a second, whereas these laser drive compression experiments are even shorter, typically having a few nanosecond duration or a few billionths of a second. And so this really presents what is a unique challenge then of finding experimental probes that can collect high quality data with really high time resolutions on these ultra fast length scales. And so, as Eric mentioned, much of my recent work has actually been carried out at what are high intensity pulse X-ray sources. And going to these facilities where we have access to ultra bright high energy X-rays allows us then to effectively take snapshots of a material's crystal structure using very, very fast exposure times down to a femtosecond or a quadrillionth of a second. And so I'll talk about a few experiments in the coming minutes. The first being experiments that were carried out at this ring type accelerator known as a synchrotron, where the primary facility that we use here is a facility known as the Advanced Photon Source, which is located outside of Chicago. And then I'll talk about a different type of experiments which use this linear accelerator, which is known as an X-ray free electron laser, or alternatively an XFEL, where in these experiments, the primary facility that we use is a facility called the Linux Coherent Light Source, which is located on the Stanford campus. And so it's really with these XFEL type facilities in particular, which is a relatively new technology, we can just get unprecedentedly bright X-rays, which give us access to really collect data at ultra fast time resolutions with really high intensity. So this is a very valuable tool, both of these types of facilities, in order to collect data during these types of ultra fast experiments. So the primary experimental method that we use at these facilities is called X-ray diffraction. And with this method, what we're effectively doing is we are studying the interference pattern that we collect when we scatter high energy X-rays off planes of atoms in a crystal structure. And so using this technique, we can effectively take a series of rapid images, which allows us to then construct a picture of the atomic level crystal structure and bonding of the material and see how that evolves during the compression and release process. So in the remaining time I have, I'm going to talk about two recent experiments that we carried out at these facilities. The first being a gun-based experiment where we collected X-ray diffraction at the synchrotron source in Chicago. And then I'll talk about some recent laser drive compression experiments collected at the X-ray free electron laser source at Stanford. So our first experiment here was a gas gun study where we looked at the shock compression behavior of SiO2 or silica. Silica is actually a very, very important material both to material science as well as geophysics. And as a result, it's been really one of the most actively studied materials at high pressure conditions. From the perspective of material science, in particular silica glass, is a very important material to understand the dynamic response of seeing that it's oftentimes used in high power optical applications. But also from the earth science perspective, silica is really important because it kind of serves as an archetype material for understanding what is the high pressure behavior of the silicate minerals that we believe make up the Earth's mantle. But also, in particular, when we talk about the dynamic response of silica, this is a very important topic of study in that SiO2 is really ubiquitous on the Earth's surface. And so understanding how it responds to shock loading is really critical for understanding and modeling things like meteorite impacts. For example, what happens when you have an impact crater, such as this crater, which is a photo of meteor crater in Arizona. So in general, for SiO2, at ambient conditions, we know that it adopts a crystal structure where each oxygen or silicon atom is coordinated by 4 oxygen ions in a tetrahedral coordination. But what we expect to happen in general at high pressure is that we'd adopt a denser structure with likely 6-fold coordination. So here we'd expect each silicon to have 6 oxygen neighbors, and this type of structure is likely to be stabilized. However, the details of the crystal structure that forms during shock loading were until recently unresolved and a topic of some debate. So in order to address this, we carried out a series of experiments where we combined synchrotron X-ray diffraction with gun-based loading at a facility known as the dynamic compression source, which is part of the Advanced Photon Synchrotron in Chicago. And this slide just shows a few photos of the experimental setup, including the length of the 2-stage gas gun shown here. And the bottom image on the left shows me mounting a target in the target chamber. And the bottom right figure shows an example of what the types of targets for these experiments look like, where a SiO2 sample is mounted on top of this brass plate under all these experimental probes. So in these experiments, what we do is we fire the gas gun, and that sends a projectile flying down the barrel towards our sample at high velocity. And what happens here is that just a few millimeters in front of our sample, there's a laser interrupt. And so when the projectile goes through that laser interrupt, that triggers the collection of a series of X-ray diffraction images, which are separated by 153 nanoseconds. So in this way, we get a series of X-ray images that are taken as the shockwave then travels through the sample and on the release. And so on the left, this figure shows results from an experiment where in this case, we shocked silica glass to a pressure of around 50 GPa or so. So here, this first image corresponds to a frame that was collected just prior to impact. The second 2 images are diffraction patterns or X-ray images that were collected as the shock wave traveled through the sample. And then the final image here was collected right after the shock wave reached the sample rear surface. And so we're starting to see a release wave come back into the material. And so from this data, what's clear is that for the first time, we're able to say that the high pressure phase that forms under this type of dynamic loading condition appears to be what is a 6-coordinated crystal structure. However, it's really interesting in that what we saw in these experiments was that there was some important and interesting distinctions in the structure that formed depending on whether we started with an amorphous silica glass starting material, which is typically what would be used, for example, for high power optical applications, as opposed to starting with crystalline quartz, which is the stable ambient phase or the mineral structure, where we were able to show very clearly that for silica glass, we observed salt crystallization of a high pressure phase known as stishovite, which is the same phase that would be observed in a static compression experiment. However, when we shocked crystalline quartz, which is the mineral that one would likely find at a place like Meteor Crater, instead we observed a 6-coordinated disordered structure. So we won't go into great detail about these distinctions. Suffice it to say that by applying these new tools, we've been able to sort of resolve some of these long-standing questions about the dynamic response of SiO2. And shed light on what is sort of a high degree of structural complexity that can occur in this type of rapid loading environment. So now I'm going to change gears a little bit and talk about a second set of experiments using laser drive compression, looking at the high pressure behavior of a material called silicon carbide. So silicon carbide is actually an important high strength ceramic that has technological applications, including things like lightweight impact coating. But furthermore, silicon carbide is actually a really interesting material in that it's a candidate material to make up the interior of carbon-rich exoplanets, which is actually a topic which has garnered a lot of recent intense interest, because in the last several years, with the discovery of a wide range of these extrasolar planets that may have chemistries that are really different than planets in our own solar system, we're very interested now in understanding how the interior structures of these types of planets with different chemistries may look. So these experiments were carried out at the X-ray free electron laser at Stanford. And here in these experiments, we mount a series of silicon carbide samples on a sample cassette, which is then enclosed in our target chamber. And then we carry out a series of shots where we focus these 2 high-powered lasers onto the silicon carbide targets, and then collect X-ray images at different probe times after the shock has entered the sample. And so effectively in this way, we're able to take advantage of what's the incredible time resolution of the X-ray free electron laser in order to sort of build a series of snapshots as the shock wave goes through the material and the material then releases. So this video here shows a collection of X-ray diffraction images that were taken for one such series of shots where we shocked our silicon carbide samples up to a pressure slightly above 200 GPa. And on the left here, we show our experimental schematic. And from this, you can see that in these experiments, we're actually using what are 6 2-dimensional detectors, which are positioned about the incident beam in order to collect maximal scattering data. However, in this video on the top, I'm only showing this top detector. So if I play this video, which I think it has started, we can see that immediately on loading, we see the emergence of new features in this image, which are correlated to the formation of a high pressure phase. And then after the shock goes entirely through their sample, we see a shift in those features, which corresponds to an expansion of that phase. And then finally, a reversion of that phase to the ambient structure on later time, once the material has returned back down to ambient pressure and the material has entirely released. So an analysis of this data reveals that similar to SiO2, silicon carbide undergoes a phase transformation from what is a 4-coordinated low pressure phase to a high pressure phase called a B1 structure, in which every silicon atom has 6 carbon neighbors and vice versa. However, in comparison to the phase change in SiO2, This change occurs around 100 GPa, so at relatively higher pressures, and also involves what is a huge volume collapse of around 20%. So as a result, this likely has both important consequences for the dynamic strength of silicon carbide, but also likely has really important implications for the internal structure and thermal evolution of a hypothetical carbon planet, possibly giving rise to things like distinct layering and flow patterns that may be largely different from the more familiar silicate planets like Earth. So I think I've been talking for over 25 minutes, so I'll wrap up just by hopefully convincing you that dynamic compression offers a really unique tool to explore material properties at these ultra high pressure temperature conditions, and is a really exciting field of study, which is developing and allowing for the study of materials at really unprecedented conditions. And also point out that, of course, these experiments involve large teams and collaboration. So this figure or photo on the left is just our team standing in front of the target chamber at the X-ray free electron laser. And this figure on the right is a photo from a more recent experiment collected remotely from our offices at the Earth and Planets Laboratory here in DC. And so I'll stop there and take questions.
Okay, I'm back. Sorry about that, Sally. That was great, Sally. That was fantastic. It was perfect. We have a bunch of great questions from the audience, and I'll also pose a few of my own. In this work, it's really interesting work, and you're basically recreating deep Earth and deep planetary conditions on the surface of the Earth by using these shock compressions. And so, of course, the shock compressions are absolutely necessary; otherwise, you can't sustain those kinds of pressures. But one of our audience members asked the question, what if you could just extend the length? So you're talking about very short, nanosecond scale compressions, and dynamics in these materials, of course, are an important part of what you see. But what if you could do a steady state, like in a diamond anvil cell up at these, like 300 or 400 gigapascals? Would it make a difference, you think, in what you find? Because that would be the core of the Earth, or the core of Jupiter even, right?
So that's actually a really interesting question, because a lot of times in these types of experiments where we're looking at what are these very fast time scales, we're concerned, for example, whether if a phase transformation takes a certain amount of time to occur, that we may not be able to achieve that type of transformation in these rapid experiments. And what we've learned in large part through experimentation is that whether we observe a phase transformation or not depends to some extent on how the mechanism of that phase transformation occurs. So for example, if that transformation involves sort of longer scale atomic motion, in certain cases, what are sort of the kinetics may prevent that from happening, or we may have to significantly overdrive that transformation. However, if a phase transformation is essentially a crystal structure just like flopping over, or a small shift in atomic positions, we know that we can observe that readily. However, there's also different experimental techniques that people have used to try to get around this. For example, one method that people have used is trying to shock a material into the melt and then sort of slowly compress it after that, which would re-solidify it. And the idea then being that you could get what would be the thermodynamically stable structure by basically recrystallizing from the melt, which would then help you overcome some of those barriers that might occur to, for example, atomic motion. And so there's some tricks that we can play to try and get there when we're worried that that may be the case.
So if I can expand that out just a little bit. So if you think about, you talked earlier about how this informs, the formation and evolution of planets like the Earth and other planets. How do you make that comparison between a shock experiment and what actually is going on? How do you validate, for example, your understanding of the minerals that you've contained in these small samples in a shock condition with what's actually going on thousands of miles below our feet, so to speak?
Yeah, so that's one of the reasons why, for example, people that do these types of dynamic compression experiments oftentimes work in close conjunction with theorists. And together, oftentimes, we can sort of serve to benchmark each other's experiments and calculations in order to sort of better understand if what we're actually probing is representative of what we'd expect to see as the energetically favored structure at these conditions. And so, I'm very lucky to have some colleagues that do calculations that I work with closely in many cases in order to sort of shine light on some of these issues. And so that's another really important key element to these types of experiments.
Yeah, that's great. I mean, that of course this explains also how science works, that you have, experimentalists, observationalists, and theorists, and it's great how that interplay really is the whole basis of discovery. Another question related actually to your samples, which is, are your targets destroyed in these very violent events that you're creating?
So that depends. In certain cases, but when we talk about doing very high pressure experiments, basically everything is turned into effectively a plasma at the end of the experiment. So in that case, we're really not collecting anything. In certain cases, for example, when we're talking about these lower pressure type experiments, there's things that we can do to effectively capture the sample. And that's really important when we're trying to compare things to like samples collected at natural impact sites and learn things about what's called shock metamorphism in minerals, for example. And so in certain cases, we can do things where we basically put sort of a capture vessel behind our target, which can in certain cases be things like a gel or an aerogel that can then capture the sample and hopefully bring it back down to ambient conditions in sort of a soft landing type way. And then we can collect that, and then we can carry out all kinds of analysis to look at the structure in a more slower manner, which allows us to characterize it much better than we can in situ.
That's great. Let me back out a little bit. Some of the questions in my own experience. So I'm a synchrotron user myself. I've spent a lot of my time at APS, a little bit at LCOS and other SSRL and others. I've also been director of Argon, so I know quite a bit about these machines. But I don't think a lot of people in the country, certainly in our audience, understand how these major facilities work, how important they are for someone like you, a scientist whose career is really dependent on these facilities. I'm wondering if you couldn't say just a few words about how important the facilities are, why they're important, and then how do you access them? I mean, these things are available for scientists from all over the country, all over the world. But maybe you could say, because these are not machines, just this machine like the free electron laser that you described, Sally, is a $2 billion machine. The advanced photon source is going on $1.5 billion. So there are a lot of taxpayer money that goes into them. They're not things that Carnegie or any university will build on their own. So maybe you could just say a few words about how you think and use these facilities.
Yeah, so I mean, you bring up a really important point in that, these facilities are just hugely expensive to both build and to maintain. So it's not something you typically have at a university or anything like that, for example. And so we really benefit from being able to use what are typically like user programs where we submit proposals and then get allocated time if our proposal is well reviewed by a committee of peers and other scientists at these instruments. And so, these are largely facilities that are supported by the Department of Energy. And so these as academic scientists, if we submit a proposal which is up to par, we basically get access to these facilities at no cost to us. And so that presents was a really exciting opportunity to be able to carry out these types of science. And also with regard to some of these higher powered laser facilities, I mean, these types of facilities are largely built by organizations like the NNSA, as well as the DOE to explore things like inertial confinement fusion. However, we can really do a lot of really interesting materials and planetary science experiments on these as well. So it's really wonderful that in recent years, they've opened up these facilities to what's known sort of as discovery science programs, which has brought in a lot of academic users, which have really applied these facilities to different types of problems, and a lot of really interesting science across different fields has emerged. So
yeah, like biology. I mean, Nobel Prizes are won for biology and chemistry all the time for discovering new proteins, or just the structure of proteins. So let me follow this up just a little bit, because you mentioned a lot of scientists using these facilities. And one of the things that that you do, of course, is you talked about the connection between pressure and core of planets, and how it's really interesting because your colleagues at Carnegie and think a lot about that stuff. What about discovering new kinds of materials, and materials that might be just fundamentally new states of matter, or something that you sort of hinted at too? What about materials that might be useful? So can you create metastable states at high pressure, that at room pressure or at atmospheric pressure would be useful and for industry or for technology?
Yeah, so that's another really interesting avenue that we can pursue with these types of experiments. Of course, one thing you mentioned is, of course, like creating high pressure phases that are quenchable, which is of course what you would need to do if you were.
So maybe you should explain to people what quenchable means.
Oh yeah. Basically, the idea being that you could transform a material into a structure at high pressures, but be able to preserve that structure at ambient conditions. So it could be used in a bulk manner for some application. And so some of the examples that I talked about, including the silicon carbide, where we formed that high pressure B1 phase, we saw that on pressure release, it reverted back to the ambient structure. So that's a case where we're not able to quench a material. However, one really interesting thing that we can learn, for example, from doing time-resolved measurements, is that we can learn about things like the mechanism of a phase transformation. So we can learn, for example, about how the atoms in a structure are required to move in order to bring one structure to another structure. So in that case, if we're able to form a structure at high pressures that might have really interesting properties, by understanding how that structure forms, we can then do things like tailor the chemistry in ways that allow us to thwart that back transformation. And so if we can understand how these structural phase transformations proceed in real time, that can give us really valuable information in order to understand how we may be able to preserve these high pressure structures at conditions like on the surface of the Earth, where we can then start to use these materials, for example. So on a really fundamental level, these types of real-time loading experiments can provide data that really allows us to study things in new ways, that can provide data that is really important in terms of understanding many of these high pressure structures and how we might begin to think about preserving them.
That's cool. So I'm going to push just a little more on the applied side and then come back to basic science, because I know that's your area of research. But this is a really interesting question about these quench states. And one question actually that was asked sort of is if you think of carbon and carbon on Earth, there's a lot of carbon down deep in the Earth. And if you think about carbon sequestration, do you think that the kind of things you're learning about, say, carbon and iron, carbon and materials that mimic the core's minerals, would also help us on the surface of the Earth to think about sequestering the carbon that we produce?
That's a really interesting question. In terms of learning how, for example, carbon can be incorporated into high pressure structures. For example, like we know in iron that you can incorporate a significantly higher amount of carbon at high pressures than you can at ambient conditions. And so the question is, if we can do these types of experiments to potentially learn how, when we release the pressure, how that carbon is actually making its way out of some of these structures, is potentially a really interesting thing to explore, to better understand, if we want to trap it, we have to know how it's getting out. So
Right.
we could potentially use these types of tools in order to explore ideas like that for sure.
Well, of course, you'd love to ultimately trap it like you trap it in diamonds. So you'd love to just trap it there for 1 billion years, right? Just leave it there and forget it. Okay, so let's move back into more basic science, but also materials. Got a lot of really interesting questions here. One which I love is are there any high pressure studies that are applicable to possible room temperature superconductivity? And this is one of the things high pressure scientists have been shooting at for a long time. So say a little bit about that, about maybe not room temperature, but high temperature superconductivity.
Yeah, so I mean, a topic which is, of course, of incredible interest, both from planetary science perspective as well as just, fundamentally understanding superconductivity, is the idea that elements like hydrogen might go metallic at conditions that are similar to something that you might expect to see in like Jupiter's core, at which point you might expect to achieve conditions where you have like things like superconductivity occurring, which is really a wild idea, of course, to think about. And really the only way to start achieving conditions like that is these types of dynamic compression experiments, because we can really only get there with these types of methods. So that's been a hot topic in the field for several years now, and is actually sort of a contentious issue, of course. But I mean, it's stuff like that's really these types of experiments. In many cases, we discover that materials behave in really unanticipated ways at these ultra high pressure conditions, where actually the original assumption back in the day was that if you squeezed everything hard enough, everything would sort of form simple structures and be really boring. But now that we have the capability to actually collect experimental data at these extreme conditions, we've shown now that there's a wide range of materials that actually behave in a really complex and fascinating ways at these extreme conditions, and both including things like their electronic properties as well as their structural properties, which are actually oftentimes correlated with one another. So, and superconductivity is just one of the topics which is certainly of interest.
Well, one of the things you mentioned was one of the questions up here, which is thinking about hydrogen, which Neil Ashcroft, of course, proposed way back in the day, 60s at Cornell. That if you pressurized hydrogen, you'd release the electrons and there would be a proton crystal with electrons flowing through. And as you point out, very high susceptibility toward superconductivity. The question actually is more around, it's sort of a dual use problem. If you can do it on Earth, the question is what's in the core of Jupiter, because that's one of the ideas for what's down at the core of Jupiter, a huge superconducting crystal of hydrogen. Do you have any thoughts on how, the pressures there are pretty high, and we're not there yet, I assume, right, in terms of getting to pressures like the core of Jupiter, or are we? Can we get there with the shock compression yet?
Yeah, I mean, in many cases, you can get to pressures that high. It's challenging to keep the temperature low enough in certain cases, because when you get to very high pressures, everything wants to heat up to an extreme level too. However, there are experiments which are sort of pushing towards that boundary. The challenge, though, is in certain cases, it's hard to make a good measurement of electronic properties at those conditions. And so typically that has to be an optical measurement. So basically you're measuring effectively kind of like how shiny something is, which is a good proxy for the electronic properties, but in certain cases can be challenging to interpret the details of what's going on for these types of very fast experiments. And so there's been quite a bit of debate as to what the actual measurements mean and how they should be best interpreted for those data sets that have sort of pushed the boundaries of what's expected at those conditions.
All right, let's see, we have a few more minutes, but I want to come back to more of the technical questions. One, which is a great question, is how do you know you're at these pressures? These are these very tiny volumes. How do you know you're getting to 300 gigapascals? How do you know that what you're measuring is uniform through the crystal and things like that? So what do you do to measure pressure is the question.
So typically what we do is in conjunction with these measurements that I talked about, which are using high energy X-ray scattering, is we also use optical lasers. And with that method, we're able to effectively measure the velocities of our sample. And we can correlate that velocity actually to pressure in our sample, because we can use effectively, conservation energy and momentum to understand how that velocity translates to a pressure in the material. And so if we're basically able to take a picture of the velocity map of the back of our sample, that gives us an idea both of the uniformity of the pressure state that we're achieving, but also the actual pressure condition that we're able to achieve in our sample. So that's typically the preferred method. Is basically it's similar to using a high-tech radar gun that a policeman might give you a speeding ticket with, but just at very high resolution.
All right, that's great. Let's see, maybe two more. One question comes back to this issue of the interplay of theory and data experiment, and I always love this one because it's always what I ask my theorist friends. When you go into an experiment, how often have you gone in with a model that predicted what you saw versus how often are you coming out of your experiment and modeling it after the fact? Do you ever get told, do any of your colleagues theorists say, go look for this at this pressure with these elements, make this mineral and you'll find X, Y, or Z, versus I found X, Y, or Z, how do I understand this?
I would say I both. I mean, I think more often as an experimentalist, I am sort of trying to get theorists to engage on the things that I don't understand in my experimental data. However, it's not uncommon to see something that you don't totally understand and find yourself digging through the literature and find some calculation, for example, that had been done of some metastable structure that you think you might be observing that had only been predicted theoretically. So I do think it goes both ways.
That's great. I mean, we can't answer every question. We could go on all afternoon. It was really a terrific talk, Sally. Really appreciate everything. We're going to show, we're now finished, so thank you very much. People can watch this, and I don't remember where, but I know that you can, if you want to come back and watch Sally's talk, there'll be a link to it at Carnegie. And I'd like to thank you again very much, Sally, for a great talk, and turn this back over to the folks at Carnegie.